Okay, so this is Dr. Kraus once again lecturing outside of class time. Stupid technology that makes it possible for me to torment you. This is a solution to quiz 1. Sorry, I will get these back to you graded before or in class on Wednesday. But here's the circuit. And so basically, first thing we got to do is combine these two resistors in series. So R23 is simply going to be R2 plus R3. And then once we do that, we can combine these four things in parallel. So I'm going to call this R1, 2, 3, 4, 5. And so R1, 2, 3, 4, 5, writing off of the page with no one to tell me that I'm doing it, is equal to 1 over R1 plus 1 over R2, 3 plus 1 over R4 plus 1 over R5. And it works out numerically. So this R23 is just equal to 500. And then this R1, 2, 3, 4, 5 works out to be, I'll throw the results of my Python code up there, but just about 60 ohms, just slightly over. So 60.61 ohms. So at that point, if I wanted to redraw my circuit, it would now look like that. So I've got my 5 volts over here, I've got R6, I've got R1, 2, 3, 4, 5, and I've got R7, like so. So if I wanted to, I could then add those three together and specifically come up with an REQ that is, R6 plus R1, 2, 3, 4, 5 plus R7, and that'll work out to 1360.61 as my final REQ. So from there, having the overall, so at that point if I wanted to, I could draw the circuit like so, with REQ here and 5 volts here and IEQ going through that thing. And then IEQ would simply be 5 divided by REQ, and that works out to, looks like 3.67 milliamps. And it turns out that that IEQ is also the current flowing through resistors 6 and 7. So I6 and I7 are equal to IEQ. And then from there I can find V6 is equal to I6 times R6, and V7 is equal to I7 times R7. And those work out to be, and of course V6 is just a little bit bigger than V7, so V6 is 2.205 and V7 is 2.573. And you notice that that adds up to slightly less than 5 volts because V1, 2, 3, 4, 5 is whatever's left, and we did a Kirchhoff loop. So we could come across that. Yeah, we could come up to that two ways. So we can say V1, 2, 3, 4, 5 is equal to IEQ times R1, 2, 3, 4, 5. But that had also better be the same as 5 minus V6 minus V7 is also equal to 1, 2, 3, 4, 5. So we could double check that if we wanted to. And so, like I said, IEQ times R1, 2, 3, 4, 5 is equal to, whoops, I typed that in wrong, the same value as 5 minus V6 minus V7. So either way, that is 0.223 volts. So there you are. So we, at that point, could go back and redraw our circuit if we wanted to, labeling a few different things. And the question is that we're trying to answer here is, how do I go back and find some of these values. So if this is R6 and R7, then we already found V6. So this is R1, R2, R3, R4, R5, and we know V7, and we also know V1, 2, 3, 4, 5. So we know those three voltages. We also know the currents. So 6 and 7 are done. So the issue is, how do I find voltage and current here? Well, it turns out that V1 is equal to V4 is equal to V5 is equal to V1, 2, 3, 4, 5. So I know that value. And so I could then say, for example, that I1 is equal to V1 divided by R1. And numerically, that will work out to what looks like 2.23 milliamps. Similarly, I4 will equal V4 divided by R4, and I5 will equal V5 divided by R5. And those numbers work out to, apparently that looks like 0.557 milliamps and 0.00. I'm sorry, well, gotta convert it to milliamps in my head. Okay, 0.445 milliamps. And then the same thing is true if we treat V2, or R2 and R3 in series. Trying to label that. So we know that V23 is equal to V1, 2, 3, 4, 5. And so I could find I23 as V23 divided by R23. And I know that R23 is 500. And so I23 works out to be, that looks suspicious. Why is it exactly equal to I5? Oh, because R23 added together is 500 ohms. And so it's the same current across both of those 500 ohm guys. And so that's 0.445 milliamps. And then it works out that I2 is equal to I3 is equal to I23. There's essentially no branches of that, so it's kind of like applying Kirchhoff's current law at each node of the resistor, but it's kind of trivial because nothing can break off. And then I can find V2 is I2R2, and V3 is equal to I3R3. And so V2 and V3 are like so. V2 is 0.0891 volts, and V3 is 0.137 volts. And if I add V2 and V3, I had better get V1, 2, 3, 4, 5, which I do. Check. So I think that's everybody. We found I2, I3, V2, V3, V1, I1, V4, I4, V5, I5, V6, and V7, and R6, and I6 and I7. So I think we're done. I will post this code. It's a little bit cryptic, so I'll explain it just a minute. But basically, it prints out the table and also prints out some of these equivalent resistances. The reason my code is slightly cryptic is I got tired of typing R1 equal 100, R2 equal 200, blah, 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 blah. So this kind of magical code up here basically creates that string for each 8 lines and then prints it and then executes that string in the namespace. And so it's basically executing these 7 lines of code without me having to type them each time. And then we're combining the 2 resistors in series, and then combining these now 4 resistors in parallel, because 2, 3 have been combined into 1. And then 3 of them are in series, and then hopefully it was 5 volts that I actually told you guys to use, or I'll have to adjust all my numbers. And then find I6 equal to IEQ, I7 equal to IEQ, use Ohm's law. Use Ohm's law on V1, 2, 3, 4, 5. Make a check that that has led to the same result as using Kirchhoff's voltage law. Then set V1 equal to that, and V4 and V5 equal to that, along with V1, 2, 3. Find the corresponding currents, and then find V2 and V3 in the way that we talked about. And then this kind of funky code just prints out the table in kind of a tricky way to make it look nice. And then this prints out some other intermediate variables that might be interesting. And so like I said, you run that and you get this output. So hopefully that's helpful. I'll see you on Wednesday.